For example number 5, there's a decathlete at the Olympics that throws a javelin such that its height h above the ground can be modeled as a quadratic function of the horizontal distance d that it has traveled. Which of the following is a realistic quadratic function for the scenario? So if we look, I've got height as a function of distance. So how high above the ground is it at any given horizontal distance that the javelin has traveled? I don't know if you guys have ever seen the movie 300, Rise of an Empire, or seen someone actually throw a javelin before, but usually you take your javelin and you throw it, and eventually it hits the ground. So it reaches a maximum height, and then eventually it hits the ground, but when you start throwing it, where you started throwing it is above the ground. So I don't have any actual numbers here, but I need to sort out what's what. What would make sense? And so if I have a parabola that looks like it opens down, that means that it has to have a negative out front, because parabolas with a positive leading coefficient open up. So I can already eliminate answer option A and answer option B because they do not start with a negative. And then again, I'm standing on the ground, but the javelin doesn't start on the ground. So when we think of our y-intercept, that starting point, that initial value, I shouldn't be beneath the ground, I need to be above the ground. So again, looking at the direction of your parabola, or the direction of the throw or the item being modeled, and then understanding where would it make sense to start at. Did it say that it was underwater? Did it say that it was at the top of a building and heading towards the ground? Was it you throwing something from eye level? That's going to help you figure out what your equation could, keyword could, look like. So if we look at this example ACT-SAT question, it says that there are abandoned mines that frequently fill with water. Before an abandoned mine can be reopened, the water has to be pumped out. The size of the pump required depends on the depth of the mine. If pumping out a mine that is d feet deep requires a pump that pumps a minimum of d squared over 25 plus 4d minus 250 gallons per minute, pumping out a mine that is 150 foot deep would require a pump that pumps a minimum of how many gallons per minute. Now that's a lot of stuff. That's a lot of stuff. Pumps pump water out of the mine. That's what we've got from the first two sentences. Water's in mines, they need to pump it out. Third sentence, the size of the pump required depends on the depth. So okay, cool. The size that I need depends on the depth. So the mine is d feet deep. That's going to require a pump that pumps a certain number of gallons per minute. And so if I know what d is, if I know that it's 150 feet deep, I need to know the y value. So I need to take this entire equation that I have here. I need to graph it in Desmos. I'm going to make a table. I'm going to plug in 150 feet for the x value, because that's my input, is the depth, and I'm going to find out how big of a pump, or how many gallons per minute can my pump out. How many gallons per minute do I need my pump to pump out? So again, I am in Desmos. I'm going to clear out the graph that I had. I'm going to go back to like 0-ish, and I'm going to put y equals d squared divided by 25 plus 4d minus 250. Again, all I'm doing is changing the input based off of the fact that d is the input in the equation, x is the input for what I'm graphing in Desmos to make sure that everything works. I've got my graph. So obviously I need to be able to pump at least 40 some gallons a minute. Maybe they don't even make pumps that don't. And it looks like my graph just goes up and 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 up. But I don't need to worry about the graph. I need the table. Because again, my question asks, what do I need if I'm pumping out a mine that is 150 feet deep? So I'm going to go ahead and go to where I can make a table. So I hit settings and table. And I'm going to plug in a depth of 150 feet. And so at 150 feet, I need a mine that can pump out, or a pump that can pump the mine out at least 1,250 gallons of water. Pardon all of the tripping over my words there. I need a pump that can pump 1,250 gallons of water per minute out of the mine. That is going to be a big pump. But again, I didn't have to actually really do any work there. I just needed to plug in the graph, look at the table, and know what I'm looking for. That's what a lot of these quadratic modeling problems are. If you have an equation, graph it, use the table function, see what you can see.